Log on, tune in, find out. Another good idea from Cambridge.
From the University Paris-Dauphine. He will speak on geodesic methods for biomedical image segmentation.
Good morning, everybody. Let's first thank the organizer for organizing this conference and inviting me. And so I will present an overview of some work on geodesic methods and especially application for biomedical image analysis. So first I will give some background, which is some rather old work on minimal paths, fast marching front propagation. And then I'll show some more recent work on anisotropic minimal paths and tubular model, and using minimal paths to find contours in images, and application to tree structure segmentation. And finally, I present some very recent research on geodesic density for tree structure segmentation. So first, minimal paths are a way to find a curve in an image, which we introduced a long time ago as a way to find the global minima of active contour energy, which means that you're looking for a curve drawn on an image that minimizes some energy, functional E, C is the curve, and P is assumed to be some feature potential that is defined on the image domain. For example, here you're looking for vessels. The vessels are darker in the image, so it's natural to consider the potential P to minimize as being the gray level, or a function of an increasing function of the gray level, which means that when curve minimizes this integral, it looks for a location where the gray level is as small as possible, which means it will locate on dark structure, which are vessels. So the input of the user is given a starting point P1, an endpoint P2, and then the output of this method will give the white curve, which is a global minima of this energy among all curves that start at P1 and end at P2. So this is not limited to this kind of images. It can be also used for contours, which means that if you're looking for the boundary of a region, you wish the curve to locate where the gradient of the image is large, and you can consider the potential P here as a function of the gradient of the image. And same thing, you give P1 and P2, and you find this red curve as a global minimizer of this energy. So what is interesting here is that it is a very fast method, and it is efficient because the problem is solved as finding a geodesic in a weighted distance metric, which means that when you look for a minimizer of this energy, where P is assumed to be positive, as I said, it can be small where you have contours or dark structure, whatever you look for. Then the first step is consider the minimal action. Given a starting point P1, you consider UP1 to be the minimal energy among all paths that start at P1 and end at P. This means that this definition is for any point P in the image domain. So here, instead of looking for a path between P1 and P2, you're looking for a path between P1 and every point in the image. The reason for that is that UP1 is, as defined, it can be looked as a weighted distance according to the metric P. And so UP1 satisfies an iconal equation that you can solve efficiently. And when you solve UP1, you can get a minimal path by second step in back propagation, which means that from point P2, you make a gradient descent along UP1, which we'll see illustrated in a moment. So the UP1 as defined is this weighted distance satisfies the iconal equation, gradient UP1 equal P, with boundary value UP1 of P1 equals 0. And the classical example, in the case P equals 1, you find the Euclidean distance the equation gradient u equal 1. So once you have solved the Cohen equation, you make this gradient descent, which can be seen as solving an ordinary differential equation, dc over ds equal minus gradient u, starting at P2, and you'll converge to P1. So now let's see what it means on a simple image. So you have here a neuronal image from which you extract some potential related to here the green channel on the image, and given a starting point P1 and end point P2, you're looking for a minimal path according to this the potential shown here, which means that it has to be the darkest possible. So you solve gradient u equal p by the fast marching method, which can be seen as a front propagation starting from the point P1 where u of P1 is equal 0, and the fast marching method can be seen as a front that corresponds at each time here. It has each curve is here correspond to a level set of the function u, which means that you have this propagation, and once you have swept the whole image domain, you stop and you get the values of u everywhere, and then you make a gradient descent, which means from this endpoint P2 you have here the graph of u P1, and by making this gradient descent you end at P1, and you follow here a minimal path according to P, which here it is shown on the original image. So this is the basic method of minimal paths. Using fast marching, it is very fast, and you can lead to real-time implementation very easily. And so more recent models based on this minimal path are especially adapted for vessels in medical or biomedical images, tubular structure, using a tubular model and anisotropic weighted distance. So the tubular model means that when you look here for a path along a tubular structure, here it has no width, so it is okay if you get this curve. But when you are looking for a vessel, then it has a width, and you wish to get at the same time the central line, and also you wish to have the boundary of the vessel. And this vessel can have a width that is not constant. So this is why the nice way to define this tubular structure is as a path in a 3D domain, which the two dimension x and y are the image domain, and you add a third dimension r corresponding to the width, local width of the vessel. So which means that a path in this 3D domain corresponds to a set of circles of center x, y, and radius r. So the set of centers here corresponds to the center line, and the envelope of this set of circles correspond to the boundary of the vessel. So now the problem is how to define a potential function and attribute potential function on this 3D domain, which means that for each value of r, here you define a potential feature value on any point in the domain corresponding to the fact that you expect to have a tubular shape of radius r at this point. So there are many ways to do that, but a simple way to see it is to look for a given point. You're looking for a circle of radius r and a circle of radius 2r, and you're looking for the variation of local statistics in these two circles. And this is a way to see if it is large or not large. It can differentiate if you are inside and well centered in a vessel, or in the background, or across a vessel. So this kind of potential can give you a good way so that when the curve here minimizes this potential, it is located where the point is in the center of a tubular shape, with, and the radius corresponds to the radius of the tubular shape you're looking for. So here is an example of vessel. So you see you have here a branch, and you can see also that the width of the vessel here is not the same as the one here. And given a starting point here and end point here, what you get using this method is a center line and the complete region of the vessel, which means the boundary of this red region corresponds to the contours of the vessel. Here, for the moment, it's a simple metric. It's going to be a Riemannian metric in a moment, but for the moment, it's just as before, a weighted distance. It means that the matrix is identity.
In XYR space.
Yes, in XYR space. So what in a moment we are going to define a Riemannian metric, which means that the potential will not be the same according to the orientation. So so here is a simple example of a U shape, and what you see here is the potential computed for different values of R, and what you see here is that the potential is the smallest where it is dark blue. So here for small r, you see that the potential is small when you have a small circle that is tangential to the boundary. It means that the circle is tangential, but it is either close to the outside boundary or the inside boundary. So you see that you have two dark blue lines here. And when you increase r, these two dark blue lines get closer and larger. And when r is a good radius here, you see that you only have one dark blue line, the two merge, and you have a darker blue here, which means here that the best location for the curve would be where the potential here is minimal. It is exactly where the radius corresponds to the radius of this shape, and the location is the center of the U shape. So here, given start point and end point, you get this center line and the boundary around. Now, one drawback of this method is that if you consider here 2 points that are far from one from the other, which means that the path will be very long, then the minimization of the energy would prefer to get a shortcut here where this is a very short path but with a high potential rather than a long curve with a small potential. So this is one motivation to introduce some potential that depends also on the orientation, which means that here you have the curve that goes in the wrong direction, is not coherent with the shape you're looking for. So now we can define a potential that is also dependent on the orientation, which will give a high penalty here if the curve deviates too much from the a priori, the prior estimate of the local orientation, which means that we're going to define an energy which depends where P feature depends at the same time of the curve location and C prime the tangent to the curve, to the path. And this corresponds to a Riemannian matrix where here you have a matrix H defined at each point in the image domain. And so this will give, this is a symmetric definite positive matrix. And according to its two eigenvalues, you will get a different value of the cost according to the direction. Which means that for the highest eigenvalue, you will get a penalty, and for the lowest eigenvalue, you will get a preferred orientation. So the nice thing about that is that you can extend the weighted distance result to this Riemannian metric, which means that defining the same way UP1 as being the minimal energy from a starting point P1 to any point P in the image, you still get an iconal equation, gradient U equal 1, but gradient U, the norm in the sense of the Riemannian metric, which means this, the metric according to H minus 1, where H is this matrix. So you have a more complicated iconal equation to solve, and you still have the same boundary value UP1 of P1 equals 0. And once you solve this iconal equation, you still get the curve as a gradient descent, but you solve an ordinary differential equation, but the gradient descent is deviated by the matrix H minus 1. So before we had minus gradient, now you have the direction of descent is deviated by H minus 1, which means that if H equals P square identity, we get back exactly to the previous case, where here you have the integral of P, and we get back to the iconal equation and gradient descent. So now with this model, what it means that if at any point you define a matrix H, and this matrix can be decomposed according to two eigenvalues, lambda 1 and lambda 2, assume that lambda 1 is smaller than lambda 2, then the unit ball according to this metric is shown here on different pixels, and can be shown, it's an ellipse, and the long axis and small axis are 1 over square root of lambda 1 and lambda 2, which means that if lambda 1 is the smallest eigenvalue, the curve will prefer to align in the direction of E1 to have smaller h at a point. It will prefer to be in the direction of the long axis of this ellipse, which means that the curve will preferably follow the long axis of these ellipses. And so we have to define a potential now that is defined on either xy space or xyr space, and also depends on the orientation. So at each point in xyr space, you define a matrix which gives you the expectation of the fact that you'll have locally a tubular shape of radius r in some orientation, which means that what we use is what called the optimally oriented flux, which basically consider a circle or a sphere in 3D of radius r and computes some kind of flow of the gradient of the image through the sphere projected on some given direction. And from this we compute a matrix H that estimates that flow for any direction, and it can be shown that this flow is quadratic form, and that can be expressed like this. And this way we get this kind of potential, which will give the best response when, once again, you are located in the good place for the good radius and also for the good orientation, which means that the local ellipses here will be directed vertically. Maybe you don't see too much here, but you'll see here better. So, so what you see here, that at the center the ellipses are more vertical than, for example, here you have circles, because there is no spatial orientation that is preferred. And when we used before the weighted distance without using the orientation, you get this shortcut. While using this oriented method with anisotropic geodesic, you get the good path, which means you get the center line plus the boundary. Okay, so this can be applied now to medical image where you have vessels. So it means that the first step in such an image is to extract the local geometry of the image using, as I said, the method based on local flux, and so, which means that at each point of the image you define this matrix, which gives the Riemannian metric, which gives both preferred orientation and preferred location as before, which means that the point will prefer to be in a darker region where you estimate that locally you have some tubular shape and in a given orientation. So all the geometry information is extracted here and then used to find the geodesic in the sense of this anisotropic metric. And so you find here, given a starting point and end point, you get this centered center line plus the boundary. And this can be also extended in 3D. So you have now a 3D plus radius space, and you define an anisotropic metric. So using this optimally oriented flux in this 4D space. And you see here a center line and the boundary of the vessel for different vessels. And you can see as well that you have a width that it's not constant, it changes along the path. So here you see another view of different vessels obtained using this method. Okay, so maybe I'll go fast on this part because the next part is more interesting, but just to say that so far we've used paths that link 2 points. You give a start point and end point and you get an open path. But in many applications in image processing, you'll looking for a closed contour, like here or here. And so we propose different ways to find a closed contour as being a set of minimal paths. So of course you could give many points on the contour and find different minimal paths joining them, but it is not what we wish to do. We wish to just give one starting point, and knowing that it is a closed contour, we automatically find a set of auxiliary points and a set of minimal paths that cover the whole closed contour automatically. So another, maybe I'll skip over this, but this is a very simple example here, just to illustrate the method that you looking for this contour. So here you have a potential that is small where it is dark, and you give a starting point here. And what you do is at the same time you do this fast marching, so this front propagation to compute the weighted distance to the starting point P1. And at the same time you compute the Euclidean length of the minimal path. So it means that for each point on the front here, if you compute the minimal path, here you'll have a long minimal path, here you have a short minimal path. So here you have an Euclidean length that is small, here it is large. So the fact is that if you divide this energy by the length, you will get the average value of the potential along the path, and the smaller it is, the better, which means that what we say is that the larger this distance is, the more likely it will be on the structure we look for. Which means that here along the front, all points here have the same energy, and along the front here you see that you have short paths, long paths. So what we say is that the first point on the front that reaches a given length will be considered as an auxiliary point, which means that a good candidate to be an endpoint, to be on the contours we're looking for. So once you get this first point to reach a given length lambda, then you go on this process starting from these 2 points, and you once again look for the first point to reach this length lambda, and go on this process till you close till the front here closes itself. This is a topological test. That when it closes, then you stop and you consider the set of minimal paths that link different points for which their Voronoi region are neighbors. So in this way you get the complete closed curve here. So here are some examples on biologic images where you give just a red point and you find automatically this set of yellow auxiliary points and the set of minimal paths here. Okay, so this is skip. And this can be applied here for tubular shape, for tree structure, where here you give a starting point, and instead of giving endpoint for each branch, here you can propagate in the tree structure like we just proposed. So you give a starting point and you add successively these auxiliary points. So you see here 4, 18, 24, and so what you see here are the different. Here you see the front propagation inside, which means that you you get here a set of points that are well. You have a homogeneous distribution of points, auxiliary points, inside the structure. And so if you use, as before, a set of minimal paths that link auxiliary points that are neighbors in the sense of the Voronoi region, then you get the complete structure. So this can be shown here. You see in red the different paths. Now the problem here is when to stop this propagation, because if you don't know when to stop, then it will cover the whole image space. So when to stop, so one way which can work if the image is not too noisy is to consider a very old tool of computer vision, which are Harris points, which are a detector for corners or T-junction. So here you see in green, these different points are Harris points. And so we applied this previous method, adding iteratively auxiliary points, and whenever you reach a Harris point, then you stop the propagation there. The local propagation is stopped whenever you get a Harris point, which means the complete propagation is stopped when you reach the whole set of Harris points, and so you will get this result here. Now, as I said, this propagation here may be in a noisy image. It may be difficult to consider the Harris points, and that's why we introduce in the last part another method that does not need such stopping criteria. But this method here can be used as shown here with regular paths or also tubular paths, which means that using the xy plus radius space, you get center line plus radius plus the boundary, and here given just a starting point, you can get here the whole set of center line for the tree structure, as well as the boundary of the complete tree structure. So here given just one starting point, but as, once again you have to know when to stop find a criteria to stop this propagation. Here is another example where you give just this starting point and then you propagate iteratively these auxiliary points and you get the whole boundary of the tree structure. So this is shown here in 3D. And finally, the more recent work is based on geodesics as well, but has the advantage that you just give one starting point and you don't need any stopping criteria or any other parameter. What you give here, so here again this is on a synthetic tree structure to show what it to illustrate how it works, and we'll see real images later on. But the idea here is to give a starting point somewhere on the tree structure and consider a set of minimal paths that go from this starting point to other points in the image domain. So a natural idea that I had first is to give all the points on the boundary of the image and consider all the minimal paths that go from the starting point to all the endpoints that are here. So if you consider here a minimal path between this point and this point, so according to this metric here, for the moment it is a simple metric, so it is small in here and large here, and since it is constant here, it means that the geodesic here will be a straight line, and then it will follow the tree structure, which means that for all points here, they will go a straight line to the closest point on the tree structure, and then follow the tree structure till the starting point. So you see that all around. Which means that you see that you have a lot of geodesics, all these geodesics will pass by this small section of the tree structure. So you see here how all the geodesics converge here to the same path. So the idea, as you can guess from the name geodesic density, is to compute a density of geodesic inside the image. So which means that here you have a small density of geodesic because you have a small number of geodesic locally that pass locally. So here, if you consider the discrete number of geodesic, you have basically one geodesic passing by here. While if you are here, you have a lot of geodesics. Basically, you have all these geodesics that pass by here. So the geodesic density will be high here. And also what you see that all these geodesics converge to this branch, and all these geodesics converge to this branch. And then these two branches add up to give a higher density here, which means that you have a very high density on the whole tree structure, and you'll have a even higher density when you get closer to the starting point, because all the branches will add up to give a higher density. So this shows this geodesic density, and what you can see is that the density on the tree structure is so high relatively to the background that it is very easy to make a threshold on this density to get the whole structure extracted. So you see here what happens on a real image, the biological image, and you see here from a starting point here in the nucleus, you get a set of minimal paths that go from the boundary, and here, I don't know if you see well, you have the high density points. So you see that you extract all the branches of the tree structure. Now, one comment here. So I talk about geodesic density. So which means that from the mathematical point of view, I mean from the continuous point of view, if you consider all geodesics ending on the boundary, then you could consider a continuous density, which means that locally you could compute this density of geodesic passing by, and you could show that this geodesic density satisfies some transport equation that you could solve to find the geodesic density. So now, from the computational cost, it may be better to consider, instead of geodesic density, a geodesic voting, which means that you consider a finite set of geodesics, and you count on each pixel you pass by, you vote, you add up the one each time there is a geodesic passing by a pixel, which means that this result here was obtained by voting using this set of geodesics. So you add one all over whenever you compute a geodesic by gradient descent, you add one, and you see that all over here you'd add one, while on this part you'll add a large number. So the voting will be larger, and this is what is shown here. So you see that you have two ways of computing this, either geodesic voting, which is completely discrete computation, or geodesic density, which corresponds to numerical resolution of a continuous formulation. So in fact, finding the geodesic density using this transport equation may be more efficient if we have more points. We have more, as we'll see in a moment. But for the moment, what we can see here is that one problem we have with this method is that you have parts of the image where you see nothing. I mean, in this part, we have no geodesics. So in this example, it's not a problem. But this example here, you see that it is a problem. So here you see that you have large region here where no geodesic passes by, which means that these branches here will have about 0, and this is why we call this a shading zone problem, which means that it's like you have a shade here and no light passes by, no geodesics pass by. So in order to solve this shading zone problem, we propose different ways, but one way is to consider different source points. So instead of getting only one start point, here you may consider different source points for which the shading zones will be different. Or you may consider the shading zone, and in each shading zone we make a second step, but this is rather complicated. Now another way is, instead of considering points from the boundary only, we may consider points from everywhere in the image. So the problem here, why you have a set shading zone here, is that you consider only points from the boundary. So there's no geodesic passing by this region from a boundary, from this point to the boundary. But there are geodesics if you consider other points over the whole image domain. So the idea here would be to consider points all over the domain, and then, as I said, the computation would lead to a very large number of geodesics to compute, and then it may be better to use to solve a transport equation. Now, even though you have a way to solve it, using a very large set of geodesics will in some way smooth the geodesic density. So the geodesic density, it will be higher on the tree structure, but it will be not so much higher than the background, which means that if you have a geodesic everywhere, you will still have a high density even in the background. Even if you have a higher vote on higher density on the tree structure, it will be more difficult to differentiate between the tree structure and the background by making a simple threshold. So what we proposed is to use an adaptive voting, which means using the idea of this voting, which means a small number of geodesics to compute, but instead of using points from the boundary, you will get a set of points that are adaptively scattered over the image domain, which means that they are scattered in a way that you have a higher density of points, of endpoints, when the potential is smaller. And this we have a way to do it very efficiently in a previous work using as well fast marching, but to propagate points on the image domain using furthest point strategy, but I'll not tell anything on that. But the idea here is that from this tree structure, I mean, here you don't know the tree structure, you know the image, you get a set of red points here, which are the endpoints that are obtained as this using this adaptive method. And so here you see that in the background, the red points are distributed homogeneously. But if you look closer on the tree structure, you'll have a higher density of these red points. And then you do the same as before. You compute the geodesics from the starting point, the source point, which is here, to all red points. And now the voting is it will be everywhere, which means that here, as before, the geodesic will be a straight line to the closest point on the tree structure, and then it will follow the tree structure, which gives here a voting that is you don't have a zero vote anywhere. You don't have shading zone anywhere anymore. So here you see this voting result, which is higher on the tree structure, and but it is not zero anymore anywhere. But still, it is much higher on the tree structures than in the background, and you have an easy way using a threshold to get the whole tree structure, including these branches that are inside. So we can see that there is an easy way to define automatically a threshold that gets a higher similarity with the original result. And since here we know the result, so and this automatic threshold can be used in real images as well. So one nice thing about this method that it is not sensitive to the source point. So we always say that we have a source point that is chosen. This is the only input that is given by the user, and this source point can be given at different locations. And you see that the voting from these three different source points is exactly the same. So it is not sensitive to the source points, and it will give the same result. And here you see extension to, not extension, you see application to real image. So here you have the source point. Here you have in red the set of endpoints that are adaptively distributed on the image. And here you have the vote, the tree structure that is extracted using the thresholded voting. So what you see here is this, I mean, this result in larger, you see it better. So you see that you get the whole structure mostly. And this is completely automatic, just given this starting point. So here another example on real images. Here are vessels in medical images. So here you see, you give a starting point, and you have here the fast marching, and you get this voting using, so you have here a comparison between different ways of consider the choosing the endpoints. So you have a starting point here, and here you use voting using all the endpoints on the boundary. So you have four sides by 256 endpoints, and here is the voting you get. So you see, because of this shading zone, you see that this branch is not obtained, and as well this branch is not obtained as well. So now if you use all points in the image domain, so you have 256 by 256, then you get some slightly different result, but still you have branches you don't get because of this there's too much information. The vote is smoothed too much. So now if you consider the adaptive voting using 1000 endpoints, but these 1000 endpoints, so instead of being on the boundary, they are adaptively chosen on the image domain, you get a very nicely easy result with all branches extracted. So, so maybe to end, I'll show just an extension of this using the tubular model, which means that you can extend this geodesic voting using the space plus radius domain, where minimal path corresponds to center line plus boundary, and then using some the voting in this xy plus radius space, so you get a voting in 3D, and then you can consider the maximum for each point xy. You can consider the point xyr, which has maximum value of the vote. And this is a way to use this voting. So here you get a starting point. Here you have the set of geodesics from an adaptive set of endpoints. And here you have the voting in 3D, 2D plus radius. And here you have the projected voting on 2D, which means at each point you have the maximum value for R of this voting. And then here, when making a threshold on this voting, you get here the complete central structure, the center line for the complete structure, as well as the boundary, which means the union of circles here, where the radius corresponds to the radius for which the maximum value is reached. So here it means that you give one starting point, and you get the complete center line for the complete tree structure, as well as the boundary. Okay. So maybe I can stop here. So.
Time for one short question.
On the shadowing problem. So let's say you do it from the boundary,
Yes.
right? The problem is some things are hidden, right? But a tree is a tree.
Yeah.
So what if you keep what you had,
Yeah.
and then when you go to the next geodesic, it just picks out the shadow stuff, so you don't have the smoothing because what you've already decided is a tree, or a piece of a tree.
I'm not sure I understood the question.
Well, maybe we should talk afterwards.
Here,
Right. So you do from the boundary, right?
I use endpoint on the other boundary.
Right.
Yes.
And you would get a part of your tree.
Yes, you get this.
All right. So you keep that. Right.
Yes.
You keep it.
Yes.
Now you have some additional points. You'll get another part of the tree.
But which are these additional points?
Whatever. But
Yeah.
what I'm saying is the problem that you had because you get too much smoothing
Yes.
would be avoided because you've already decided on trees at each
Well-
step.
Okay.
By taking pieces of trees at each step, you're avoiding the smoothing problem.
Yes, but in fact, I'm not sure, but I think this is corresponding to this second step in each shading zone. In fact, I didn't insist on this part, but another way is to, for each shading zone, we consider points on the boundary of this shading zone, and we start again. Does it correspond to what you expect, or? No?
Maybe we transpose that to
Okay.
the coffee section. And maybe
Yes.
I don't know, there's another. Very short.
A quick question. How does it perform on noisy images? It should be somewhat robust, no, towards noise.
It should be?
It should be somewhat robust when you have noise, no? But I'm not
Yeah. Because since you have a lot of geodesics, it's somewhat robust to noise, but it depends in which way, because it depends which kind of noise. I mean, noise in the image is robust, but noise, there's another kind of noise to which it is not robust, and you may give a post-processing afterwards. It is this kind of noise, I mean, which not real noise, but noise in the fact that you have information that is not interesting. So here in the vote, all geodesics that pass by here will connect to the center, and will create an artificial vote here and an artificial branch here. In this way, it is some kind of noise that is not really noise, but because the background noise here is not too much sensitive, but this kind of information can be considered like an important noise. And for this, you may, in the second step, post-processing on the set you have here, in order to remove some branches that have low energy.
Okay, so thank you again.